All right, everybody, let's get started. It is time for the Virtual Science Cafe, brought to you by the North Carolina Museum of Natural Sciences. Thanks for tuning in tonight. Thanks for joining us. So glad that you're here to learn something new. Hope you brought your thinking caps. Hope that you got some snacks to get ready for our Science Cafe right here on YouTube, right here on Facebook. We're all over the internet this week. This is a very special week for us at the museum. It's Earth Week. That's right. Yesterday, April 22nd, was the 50th anniversary of Earth Day. So we decided to stretch the celebration out as much as we could. We've been having guest speakers every day this week, Monday through Friday, sharing with us their science, their research, their passion for the planet, or in this case, with our virtual science cafe tonight, their passion for this planet and other planets. So thanks for joining us. Glad that you're here. Thanks for tuning in. As we go along in tonight's program, feel free to use the chat box, the comment box, to leave questions and comments for our guest speaker. I will ask that you be respectful of our guests, of course, and respectful of one another. My name is Chris. I am your host every Thursday for the Science Cafe. Normally, we have our Science Cafes in the middle of beautiful downtown Raleigh at the museum at the Daily Planet Cafe. Of course, events being as they are, we can't exactly do that. So we've brought the program live online. My very special guest this evening is a planetary scientist from North Carolina State University. Please welcome to the show, Dr. Paul Byrne. Hi, Paul.
Hi, Chris. How's it going?
I'm doing pretty good, pretty good. How are you?
Doing pretty well, all things considered.
Yeah, all things considered, sure. How are things on your side of North Carolina?
Just things are okay. Things are okay right now. You know, we're getting by.
Good, good. Glad to hear it. Glad y'all are doing well. So tonight we're going to be talking a little bit about Venus and Earth. And, you know, I guess on the face of it, it seems a little odd to talk about other planets for an Earth Week thing. What do you think about all that?
I think one of the things that we've seen as planetary science and planetary geology has become a thing we've been studying for the last few decades is that the more we understand about other planets, the more we come to understand about our own planet. So, in fact, I think there's no better time than Earth Week, Earth Day, for us to really kind of take stock of what we know about this world and what other planets can tell us about the future and potentially the past of our own world. I think that's really important we get that broader context. So I'll talk a little bit about that in my talk this evening.
I think I'm ready to learn. Everybody watching, I hope you're ready to dive in. Let's get started with the Virtual Science Cafe. Dr. Byrne, take it away.
Thank you very much. Okay, I'm going to share my screen. I just want to make sure that you can see it right there.
It looks excellent.
Okay, cool. Thank you again, Chris. It's lovely to be here, and good evening, everybody. So yeah, as Chris said, my name is Paul Byrne. I'm a planetary geologist, and one of the things that really fascinates me and makes me want to understand the universe is I want to understand why planets look the way they do. And it turns out that there's a planet that's very, very unlike our own in some respects, but also very similar right next door, and that's Venus. And so in this talk, I'm going to try and answer, or at least address, a question. Does Earth show us what ancient Venus once looked like? And does Venus today show us what future Earth might look like? So that's kind of what's driving us here. Venus is a world that is fascinating. One of the most compelling science questions we have right now in planetary science is, why is Earth's sister not its twin? And what I mean by that is, if you look at Venus, it is almost the same size and almost the same mass, almost the same density as Earth. It's about the same age. It formed around the same star. It's made of the same stuff. But what we know today, and I'll describe this in a bit more detail in a few minutes, is that Venus today looks absolutely nothing like Earth. It is so vastly different in terms of what it's made of, and its atmosphere is so different. The surface features, even the conditions on its surface. But it is worth pointing out that this is something we've only come to learn in the last 50 years or so. For a long time, hundreds of years, astronomers figured that Venus really not ought to be that much different to Earth, because if you look at how warm Earth is as a function of our distance to the sun, Venus is not that much closer. And so for a long time, people thought that maybe Venus is a world home to lush jungles and exotic creatures and all kinds of weird looking landscapes that though alien, would not be totally dissimilar to our own. These are two examples of Pulp Fiction comic book covers for the 1950s, as recently as the 1950s, in which you can kind of see what people thought these fantastical images might be to represent Venus. We have these kind of exotic creatures flying through the sky, and sure, the sky is kind of a yellow color because we know that Venus is a kind of yellow glow. We see it, the evening star or the dawn star, but you can see there's some sort of weird, pterodactyl looking thing and some sort of Loch Ness thing and weird plants and Venus flytraps because, of course, it's Venus. Unfortunately, Venus is nothing like this, at least not today. But we only learned that a few decades ago. And that really kind of put paid to our idea that you could simply predict what you'd find on the surface of a planet only as a function of how far it is from its star, and therefore how much sunlight it's getting. And so that kind of poses the question that I asked a moment ago: why is Earth's sister not its twin? How do you get two worlds that are, on the face of it, pretty similar, but actually vastly different geologically and in terms of their atmosphere? So it's worth kind of talking about what Venus is. It's an Earth-sized world in the habitable zone of its star. Habitable zone is a phrase that planetary scientists and astronomers often use to try and describe the area around a star where water is liquid on the surface. Right? There's a lot more nuance to it, and often it's not used in the right way. But generally speaking, if you're in the habitable zone, at least that's the first box ticked for a world that might be Earth-like, that might be able to hold life. And I say here that it's an Earth-sized world in the habitable zone because, given the ability we have to detect planets in other star systems today, so-called extrasolar planets or exoplanets, we don't have the ability to distinguish planets that are so close in size as Earth and Venus are, which means that if you're an alien astronomer 40 light years away looking at our star system through your telescope with your little squiddy arms or whatever kind of alien you are, you cannot tell Earth and Venus apart. They're effectively the same size. So when you hear people describe an Earth-sized world discovered in the habitable zone of another star, you can replace the word Earth with Venus and not be incorrect. So Venus is an Earth-sized world in the habitable zone. And if we look at some basic data for Venus, we see that it is, let's see if this comes up here. It's about 82% of Earth mass. It's 95% the radius of Earth, so it's a little less dense, but it's almost the same size and same mass. And it orbits at 0.72 AU. 1 AU, or astronomical unit, is the distance, the average distance between Earth and the Sun. So if you're 0.72, you're about 70% as far from the Sun as we are. So not that much closer, not even half as close. In 1962, the big Goldstone radio antenna on Earth determined that, in fact, really quite curiously, Venus orbits around the Sun the same way we do, but it rotates on its own axis backwards. We don't know why that is, but if Venus had a magnetic field, which it doesn't, and you were to set north in the same way that you would on Earth, you would see that the Sun rises in the west and sets in the east. So we don't know why that is, but it's one of the weird mysteries of Venus. And the first interplanetary flyby of a spacecraft that we sent from Earth to another world was to Venus. Mariner 2 by NASA in 1962 flew past Venus. It wasn't able to make orbit, so it just went past once. But that one flyby was the first time we successfully dispatched something to another body that wasn't the moon, that was another true planet. You might know a lot about the fact that we're exploring Mars today and we're sending spacecraft to the outer satellites and we're going to asteroids. But for a long time, although sadly not for the last 30 years, but for a long time, Venus was the premier target for NASA and for the USSR. But in 1962, Mariner 2 flew past, and it had a set of instruments on board that were able to take some measurements through the clouds from space onto the surface. And one of the things that Mariner 2 sent us back that shocked us was that the surface of Venus is totally unlike what conditions you would expect if it were a warm, moist jungle world. In fact, it's extraordinarily hot. We'll come back to that in a moment. There's also no resolvable magnetic fields, which is strange because a world as big as Venus, we might expect that it generates its own magnetic field as Earth does, and yet Venus does not appear to, and we don't yet know why that might be. The sky of Venus is both lethal, and by that I mean that it's almost fully CO2. It's got a very high DH ratio. That's something we call a high deuterium to hydrogen ratio, and I'll come back to why that is important, and it's really important later, but its ratio is about 100 times higher than the corresponding ratio on Earth. It has a super rotating atmosphere, and that is essentially what it sounds like. The atmosphere rotates faster than the ground does. So although the winds are very calm in terms of the speed of the surface of Venus, their force is tremendous, and we think that wind plays a very important role in shaping what we're seeing on the surface, at least chemically. We also know there's a global layer of clouds, and unlike water vapor clouds like on Earth, those clouds are made of H2SO4, which is sulfuric acid. So there's several ways in which Venus will try and kill you, and one of the ways it will do that is with its global layer of sulfuric acid clouds. But we know a lot about the atmosphere, or at least we know something about the atmosphere of Venus, because in the 1980s, the Soviets flew 2 balloons, Vega 1 and 2, about a couple of days apart. And those balloons were dropped off into the atmosphere by spacecraft that then went and left Venus and went off to Halley's Comet. And they operated for about a day or so before their batteries ran out. And what these balloons showed us at an altitude of around 55 kilometers, which is about 35 miles, that in fact, in some respects, conditions are almost Earth-like, which is telling. And so when I say the sky is both lethal, it's also fairly hospitable. If you happen to be about 55 kilometers or about 35 miles up, it turns out that it's almost room temperature conditions. It's a little cooler than room, but you can put a jacket on, you'd be okay. The pressure is about equivalent to being about 18,000 feet up, which is maybe a little more than half the height of a commercial airliner. So you're still going to need some amount of air unless you're very fit. But we have people who are at 5.5 kilometers or around 3 miles up, and they can be okay. So certainly you could be okay as long as you had an oxygen mask or an oxygen tank of some kind, because it's still a CO2 atmosphere. But it even led NASA to look into a thing they called the HABOC concept in 2015. And lots of other people have proposed variants of this, whereby you could safely operate humans. You could have humans safely operate machinery if they were able to live in these gondolas beneath these huge floating dirigibles, maybe 55 kilometers over the surface of Venus, which would be remarkable. And it probably wouldn't look all that dissimilar to being above the clouds on Earth, except that you're much, much higher. But you'll notice that the clouds here, this is an image from Earth into which these computer-generated rendering of what these things might look like. So this is really an image of Earth. It would probably be a little yellower if it were Venus. And instead of those nice puffy water clouds, you would have sulfuric acid clouds. So again, not somewhere you want to kind of go to. You want to make sure that you're not going to have an unfortunate incident where your dirigible deflates or something. So we've got a sky that's lethal chemically, but at high altitude, it's not that inhospitable. But the surface is hell made real. There's nowhere else in the solar system like this. In fact, the surface of Venus is hotter than the surface of Mercury, which is closer to the sun. In fact, we know that the temperature of the surface is that of a self-cleaning oven. It's about 470 Celsius or 740 Kelvin. It's the temperature your oven goes into a self-cleaning cycle. That's the temperature all the time. And because the atmosphere is so thick, the pressure is equivalent to being about half a mile under the ocean. It's about 90 bars, 90 times room pressure. As a function of that, it means that because the atmosphere is so thick and moves slowly around the world, although the atmosphere does move faster than the ground, right, hence the super rotating part, it means there's no real temperature difference at all between the poles and the equator, quite unlike Earth or really most worlds. So it's kind of that same hellish temperature everywhere. It gets a little cooler as you go up, but a little cooler by a few tens of degrees, not anything meaningfully cooler. However, we have been on the surface of Venus. However, briefly, we know that the surface rocks are basaltic. They're made of basalt. This is the most standard rock you can get. If you look for rocks somewhere in the universe, chances are it's basalt. It's what the surface of the moon is made of. It's what the surface of Mercury is made of. It's what the surface of most of Mars is made of. It's what the ocean floors are made of on Earth. And it's most of the surface of Venus. It's basaltic material. And that tells us that, for first order, the stuff that's inside Venus is pretty much probably the same stuff as inside Earth. And that is important. And I'm going to come back and illustrate that for you in a moment. One of the really exciting things that I think humans have achieved is in the 80s, the 70s and 80s, the USSR was able to land a series of landers on the surface of Venus. Now, these things are about 5 or 6 feet tall. And you might even see, this is a kind of a rendering of one sitting on the surface, but most of it's this kind of big pressure ball, because this thing is under severe pressure, but it's also full of wax, because it has very delicate instruments. And as you've ever used your phone on a hot day, those things do not like operating under high temperatures. So imagine trying to run instruments and self-cleaning oven temperatures. So these poor landers only lasted about 2 hours. But that was enough time to get some images of the surface, to tell us what the surface was made of. Grossly speaking, that's what we know they're made of basalt. In fact, Venera 13 and 14, both of which landed a few weeks apart in 1982, even took the first recordings of sound on another planet, which is pretty cool. You can go and you can find those on YouTube. And you can hear this kind of eerie whistling of the sound of the Venus wind whistling over the landers, which I think is pretty neat. But then those landers were killed because the surface temperature is terrible. So one of the worst places to be in the solar system is certainly on the surface of Venus. And of course, that makes it really hard to explore Venus, because Mars is a lot more nice. And you can land stuff and have stuff operate for years on Mars. You cannot do that, Venus. One of the things that we've learned over the last few decades about Venus is that although in some respects it is very similar to Earth, it does not have plate tectonics. And I'm going to describe in a moment why that's really, really important. It does, however, have what we think is a differentiated interior. This is a term that we planetary scientists use to say that when a planet gets made, if the planet's big enough, as it's very, very hot soon after it's formed, all the heavy stuff is going to sink to the interior and all the light stuff is going to rise. It's the same idea that if you took a test tube and you filled it with water and sand and you shake that test tube, after a minute or two leaving it standing, the sand will settle out and the water will rise up. That same concept applies to how planets form and how they develop, which means we think that the layers inside Earth are pretty much the kind of layers you see inside Venus, if we were able to cut it open. Unfortunately, we cannot land seismic instruments on the surface of Venus. We know through seismicity that's what the inside of Earth looks like. So we have to make guesses as to what the inside of Venus looks like, or rather we know what Earth looks like because of seismic instruments. So the big question we have is, we don't know this for sure, but we think it's going to look similar to Earth. Yet despite that similarity, it doesn't have plate tectonics. It doesn't really have evidence for stuff moving on the surface the way Earth does. But we do know that there are places where there's volcanoes. We don't know if they're active, but we see photographs of things that look like volcanoes. We actually can't photograph the surface of Venus space the way we can Mercury or Mars or even Earth. So we have to use radar. And so that means we got to process it a bit differently, but we can still look at the surface through the clouds with radar. Light, normal visible light cannot get through those thick clouds, radar can. And on these radar images, we can see things that look like volcanoes and things that look like lava flows. And we see volcanoes and lava flows on Mercury and Mars and on the moon, so it's not surprising that we would see them on Venus. We know that some places where we see volcanoes, they correspond to what areas we call mantle upwelling. So we think Earth's mantle moves, it convects, which is the same idea as watching water bubble in a saucepan you put in your stovetop. Some bits, the hot bits come up and the cool bits go down, relatively speaking. We think that's happening in Venus's mantle. That's the key process that drives plate tectonics on Earth. We don't see plate tectonics in Venus, so we're not clear why. But where we get the mantle coming up on Earth, we often get volcanoes. And we think that's something similar to what we're seeing on Venus. So in that respect, it's similar to Earth. And in 1990, NASA's Magellan mission arrived at Venus. And we had some radar images before then, but Magellan kind of changed the game because over about 4 years, Magellan was able to image the entire surface in radar. And that really gave us a sense of what the surface looked like in a way that we hadn't appreciated before. We saw that there are some low-lying bits, there are some high-standing parts. We saw that in some places, the crust is thicker. We can make guesses on the basis of those measurements we have. The areas that are thicker appear to be higher, which is not dissimilar to Earth. So we're seeing a long list of things geologically and geophysically that Venus has that's just in common with Earth, and yet still does not look like Earth in terms of plate tectonics. Right? This is Earth. This is a cross-section of what we think plate tectonics looks like on Earth, where in the oceans we have what we call spreading centers where new oceanic crust is made. And these oceanic plates slowly move in a conveyor belt fashion all the way over to what we call subduction zones, where that material subducts back into the interior. Plate tectonics is an important, really, really important process on Earth, because one of the things that we think plate tectonics does is that it keeps Earth cool. As plates generate new crust, and this crust moves to the oceans, we have a lot of carbon dioxide in our atmosphere. In fact, one of the things we're seeing with human-driven climate change is that we cannot draw that CO2 down fast enough. But over geological timescales, if you exclude the human contribution, that CO2 gets drawn down into trees, but it also gets drawn down into rocks. For example, little creatures in the sea will convert some of that CO2 into their shells, and then those creatures die and the shells fall to the ocean floor. And as that ocean makes its way, that ocean floor makes its way over to a subduction zone, eventually that carbon gets brought back into the inside of Earth. It might take tens of millions of years, but eventually Earth is able to bring right back inside itself the carbon that it previously liberated. This is one of the most important things Earth can do because it will keep Earth cool. It'll keep Earth's temperature approximately the same, with plus or minus a few degrees, even a few tens of degrees, but over hundreds of millions of years, Earth is able to regulate its temperature. I'm going to come back to that in a few minutes and why that might be so important to Earth's history and why it might have been important to Venus's past. So just like Venus, we have a differentiated interior. All the really heavy stuff like the metals are in the core. We have this active recycling of surface materials. Stuff on the outside will come back down again at some point as it's drawn into the interior. And new stuff will come up here, these spreading centers we have. All right, back to Venus. One of the things that really surprised us by Magellan, which was this radar mission that kind of gave us a view of the whole surface. This is a computer-generated image of what it would look like if you were kind of flying over the surface. So you can see that things get hazy in the distance because the atmosphere is very thick. But what really surprised us is that although there are craters, And here, again, this is a kind of computer-generated image from radar data. So it's not really what your eye would see, but we can see holes, and we see radar bright areas on radar data tell us they're rough, and this is impact ejecta, all this stuff thrown out during the impact. So it's not surprising that it's rough. And we can see one here in the distance, and there's even one over here in the far distance there. But what's interesting about this is that there's only about 900 craters on Venus. That's not very many. There's about the same number on Earth. But on Earth, we have plate tectonics, and we have weather, we have water and oceans and trees and vegetation and human activity. So craters don't last all that long geologically on Earth. Even meteor crater, which is an astounding thing to go see, is only a few tens of thousands of years old. It's not billions of years old. So it was really surprising to find only 900 craters on Venus. We would have thought to find tens of thousands, just like we see on Mercury, just like we see on Mars. None is below about 3 kilometers or 2 miles in diameter. And we think that's because the atmosphere is so thick that the atmosphere protects the surface of Venus from objects that would be able to make impact craters 3 kilometers or below. But what's really interesting is that the distribution of impact craters across Venus is indistinguishable from random. And that's a really important phrase that we scientists use. Craters form randomly anyway. But if you had a planet with different geological processes taking place, you might find some areas with lots of craters and some areas with not many craters at all. There'd be quite obvious differences in the number of craters because different things have happened to different parts of the planet at different times. But Venus's craters, look, they're kind of distributed all around the same time, which kind of made people think, it still does, that maybe the surface is all the same age. Now, it's probably not that easy. It's probably not that simple. But we certainly do not see a distribution of craters on Venus that we would expect elsewhere. And one thing we really don't see on Venus are absolutely giant impact basins, right? We use crater for things that are a few tens of kilometers across, perhaps. But when we talk about really, really huge holes in the ground, we call them impact basins. And we see lots of them in the solar system, but there is none on Earth left. Presumably Earth had them because the moon has them. But the ones on the moon are 4 billion years old. We see them on Mercury. We see them on Mars. We don't see them on Earth, and we do not see them on Venus. And that really does contrast to what you see on the moon. For example, this is the moon, exaggerated colors. You can see the different lava flows and stuff. But this is a huge impact basin on the moon called Imbrium. You can see it on the lunar near side, the side facing us. It's about 700 miles or 1,100 kilometers across. It's 4.1 billion years old. Nothing like that preserved on Venus, just like on Earth. So something or some combination of processes has been able to bury and obscure and remove the really, really ancient stuff that Venus surely had to have had. Surely Earth had to have had. Some active process or combination of processes that removed them. We don't know what process that would be, but we have a leading contender, and that's volcanism. In fact, it would be surprising if Venus was not volcanically active. But I want to kind of stress here, we do not know for sure. We have not yet flown a mission that would be definitively able to show this. So we have to kind of make inferences from the data we have. But I, for one, think that Venus is surely volcanically active. It's probably volcanically active right now. How can you have a world almost as big as Earth, which is volcanically active and not have volcanoes? There's a few things that support this idea. We had a mission that the European Space Agency flew to Venus in the 2000s called Venus Express. We got there in 2006. Venus Express, it was not explicitly designed to look at the surface. In fact, it certainly wasn't looking for volcanoes. It was mainly looking at the atmosphere, but it was able to detect short-lived hotspots on the surface through the atmosphere. And one way to explain a bit that gets hot and then gets cool again, relatively speaking. I mean, relatively to the fact that the whole thing is hot. But a hotter part may be explainable in terms of volcanism. There's also high emissivity. That's something that the radar tells us. Emissivity is a function of how bright it looks. And one of the reasons it's bright is if it's rough. But another reason is if it's relatively fresh. Recent lava flows on Earth have high emissivity. And we see high emissivity lava flows with radar data on Venus. So maybe that tells us that those flows are relatively recent. And I don't know how relatively recent it is because we don't know. We don't know the ages. But relatively recent meaning the last few tens of thousands of years, which to a normal person is not recent. But to a geologist is very recent. So that would be exciting. There's also the fact that the amount of SO2 or sulfur dioxide in the atmosphere seems to not be the same all the time. And SO2 is one of the several gases that come out of volcanoes. So that might tell us that there's been volcanic activity happening. So this is a massively open question, but it does raise the possibility that there may be active volcanism, volcanic activity taking place today. And volcanism is extremely effective at pouring out huge amounts of lava that would cover the surface and might potentially explain why the surface of Venus looks geologically young. Now, I mentioned a little while ago that one of the interesting things we detected from those earlier missions to the atmosphere of Venus was that we detected a a high D to H ratio, a deuterium to hydrogen ratio in the atmosphere of Venus. The reason this is important, we think, is because that ratio basically tells you how much water a planet has lost. And if Venus has way, way more D to H in terms of deuterium to hydrogen than Earth does, Earth still has a lot of water on the surface and a lot of water in its atmosphere. There's no water on the surface of Venus, and there's only a bare trace of it in its atmosphere today. But the fact that the D to H ratio is so much higher meant that early on people proposed that perhaps Venus once had much, much more water than it does today, and it lost that water. And if that's true, it raises the sort of tantalizing idea that at some point back in the geological past, and we don't know when this is, but it could be as recently, and I use that term loosely, recently as 1 billion years ago. Again, that's not all that long ago for a planet, or perhaps 3 billion years ago. It's possible that Venus once had oceans of liquid water on its surface. And it raises the possibility that this is a CG, a computer-generated artist impression of what a water world Venus would look like. But it raises the possibility that at least for a time, a long, long time ago in solar system history, there may once have been two Earth-like planets, two worlds like Earth is today. A blue world seen from space with white water vapor clouds, not the sulfuric acid clouds we see today. Now, we don't know if the surface was green, because on Earth green is chlorophyll. It's a biological process. Life makes the green stuff, so it might have been brown. But the point is that for a while, there may have been two blue marbles, not just one. So we'll be celebrating 2 Earth days, not just one. Now, we don't know this is true, but it kind of comes back to this question I asked at the beginning. Why is Earth's sister planet not its twin? Do these planets have a shared history in terms of not just how they formed, but what their conditions were like on the surface for a while? And if they don't, why not? That seems like a pretty important thing to be able to answer, right? How do you get two worlds that are on the face of it the same, and they go down two vastly different paths? And if they did, in fact, have that same shared origin, when did their paths diverge and why? And that gets to the last bit I'll talk about in this talk, which is it possible that in addition to present-day Earth showing us what perhaps ancient Venus would look like, might present-day Venus show us what future Earth would look like? This gets to the idea that things do not stay the same forever. And things, even over billions of years, do change. And in fact, what's interesting is a few billions of years ago, the sun was much fainter than it is today. It turns out that a natural thing that all stars do is as they burn their fuel, they get hotter and they get brighter. And this process is very, very slow. It does not affect climate on any meaningful scale that we can relate to, but it does affect climate over hundreds of millions and billions of years. And it turns out that about 4 billion years ago, the sun was perhaps 70% as bright as it is today, comparable to what the surface, what the sunlight that Venus gets today. And so if you were on Earth, things would look a bit darker. It would be not totally unlike when we had that amazing total solar eclipse in 2017. And so you get this idea that maybe 4 billion years ago, it's 30% less bright, and so there was much less energy reaching the surface. And since sunlight is a key modulator of how much energy we have and how much heat we have on the surface, the idea is that over time, as the sun brightens and it gets hotter, the so-called habitable zone, remember that was this idea that if you go a certain distance from a star, you have a region where water is liquid and stable as liquid on the surface. Well, the idea basically is that through time, and it's kind of illustrated here in terms of temperature on the y-axis here on the left-hand side of this graph, this could either be different stars, but it could also be our star changing temperature, getting hotter through time. And it means that the distance you are from it will change in terms of where that water is stable. And one of the consequences of that is, as you get hotter, as your star gets older, the amount of energy you get, which is basically everything between these two lines, the red and blue line, the amount of energy you get in your surface will go up. And eventually there'll come a point when, even if you've not moved and your star hasn't moved, your star is now putting out too much heat, too much solar energy reaching the surface for water to be liquid on the surface. And if that happens, then you start to be in big trouble. Now, we're a long way from this happening, but this may exactly be the reason Venus is so different to Earth today. So basically what happens is, over time, the sun gets hotter, it gets brighter, and we get exposed to more and more solar radiation. And eventually, and I mean over 1 billion or so years, an extraordinarily long amount of time, eventually the amount of energy reaching us will make things hotter, and it will begin to effectively evaporate water off the oceans. I mean, that's what we call the hydrological cycle anyway, because we evaporate water from the oceans, it turns to rain, it comes back on the ground, flows through rivers and back into the sea, so it's a cycle. But if you have higher surface temperatures everywhere, both on land and on the sea, you'll evaporate more and more water, and your clouds will get bigger and bigger, and your world will start to feel kind of tropical everywhere. And the more clouds you have from this evaporation over the seas, the more energy you're going to start to trap, because clouds will trap that long wavelength radiation. That's the idea of this kind of greenhouse effect. And eventually you might actually trigger a critical point called a runaway greenhouse effect. And this is sort of the worst case scenario for a planet. Because what will happen is that you will start to gather so much energy that you will evaporate all the water in the oceans. You won't lose the water from the atmosphere necessarily, so it might still rain, but as soon as it rains, it's too hot on the surface and it will evaporate again. And if that happens and you boil off Earth's oceans, the problem is, and this might only be as, billion years isn't that old for a planet, it's only 4.5 billion years old. If most of your surface water is evaporated, plate tectonics stops. Plate tectonics is one of the key things that allows it to happen on Earth, is that water weakens rock and makes it easier for plates to slide under each other at subduction zones. That's where we're bringing stuff from the surface and driving into the planet's interior. If you don't have liquid water on the surface, you don't lubricate your plates. And we think plate tectonics will stop. And if plate tectonics stops, then Earth, probably only over a few 100 million years, which again is not all that long for a planet, will rapidly come to resemble Venus, because all the volcanism that's happening inside Earth is going to happen anyway. All the heat, all the lava, all the CO2 that volcanoes put out, but it won't be able to go back in. That CO2 won't be locked into the interior again. The lava is going to build up and come out, but it won't come out necessarily in the controlled way it does today at subduction zones and at different places on Earth where plate tectonics controls volcanism. It might come up anywhere. In fact, if this process continues happening with plate tectonics stopped, you might get a huge outpouring of lava in one place and a huge outpouring of lava in another. And over time, you may actually end up resurfacing the entire planet. You won't bring the CO2 the volcanoes have put up that the little sea creatures is to bring down to the ground. You won't be able to withdraw that. So you'll have a very, very thick CO2-rich atmosphere. You'll have an extremely arid surface, just like Venus is today. And in perhaps 2 billion years, the entire surface, there won't be any distinction really between land and sea anymore, and the entire surface will be dominated by widespread volcanic flows. And you will have effectively turned Earth into Venus. So if that's true, well, short answer is we don't know if it's true. We have a good model, and most of the data satisfy the model, or the model satisfies most of the data, but we don't know. And that kind of is dictating what we need to do next as planetary scientists and as people in general to try and understand why our sister isn't our twin. We need to have better understanding of the composition and the evolution of the atmosphere and of what the surface is made of. We need to understand what the inside really looks like. Really, does it have the kind of interior structure that Earth does? We also want to know what kind of activity there is. Are there quakes? Are there Venus quakes? Is there active volcanism? The reason this is important is because it's important that we understand Venus in its own right. We go and explore Mars to understand Mars. We explore the Moon or Mercury to explore and understand the Moon and Mercury. We should understand Venus just as a whole planet by
Paul, did we lose you? Oh no, everybody. I think we lost Paul. Oh, man, we were just getting good to the good parts, weren't we? All right, we're going to work as diligently as we can to find our planetary scientist somewhere on the internet. But I'll go ahead and remind you, since I think we're getting close to the end, go ahead and put your questions, comments, thoughts for our planetary scientist, Paul Byrne, there in the comments. If you're watching on Facebook, if you're watching on YouTube, and when we do get Paul back, we'll post those, pose those to him, and see what he thinks about your thoughts. But since we're here and while we're waiting, let me know what you're thinking. Ancient Venus, future Earth? We can go ahead and start the conversation right here. Maybe you think it's just wild that the surface of a planet, not too much like ours, would be what, 800, 900 degrees Fahrenheit? Could you even imagine? I say that there's a few questions coming in, and this is great. Like, what killed the original landers on Venus's surface, and how did they die? My guess, and we'll have to ask Paul if he makes it back, is that it was just too hot and too much pressure. He talked about how they tried to build to withstand temperature and pressure, but ooh, that is a lot going on there. Ancient Venus, future Earth. So, what about future Earth? What do you think about this idea that eventually one day Earth could end up looking just like Venus? You know, that digital image of Earth completely void of water, no more water left. That kind of got me. Like, the explanations seem really solid for how this can happen and how you get a planet like Venus and how that could happen for a planet like ours. So I need some hold music and a little video to play for you because Paul's trying to get back to us. Okay, I got a message. He said they had a huge power failure. So we'll see if we can get him back. In the meantime, I know you've got questions. Post up. Let's hear it. What are your thoughts about what you've learned so far? If you could visit the planet Venus, if somebody said, we'll give you a temperature and pressure safe suit, and you get to walk around on the planet Venus, would you take it? Do you think you'd want to explore those sulfuric acid clouds? What about that 400 plus degrees Celsius surface? Let me know what you think in the comments. And
Hello.
Paul, did you make it?
Yes, yeah. I was like, of all time, we haven't had a single power cut in the time I've been working from home. You asked earlier how things were fine. Well, things were fine until we got the power.
Right until right now.
Yeah.
You made Earth angry.
I clearly did. I really shouldn't have been talking about how our planet's going to be killed by the sun. So I'm sorry. I take that back. But it looks like things are good for now.
Now you're going to have to go back and undo all of the wrong things that I said about Earth and Venus while you were gone. But I'm not going to tell you what they were. We'll just let it come out in the wash.
That's fair. That sounds good. And honestly, we don't know that much of Venus. I'm just making it sound like we know more than we do. So it may not be wrong.
But you know more than I know about it. And that's what's important right now. So you were telling us about next steps in research.
Right. So if I can, let me just go and share this part of it again. I should be able to share my screen. And let's see if I can. So can you see the slide we were on just before we got really interrupted?
Yes.
Okay, cool. So basically what I was saying is just to finish up the talk, is that we understand, we explore other worlds to understand them in their own right. And there's real value in doing that because it just helps us understand why we see what we see in the solar system and the universe at large. But Venus is, I think, extra special because it's not just Venus we'd understand if we study Venus, because it turns out that it will help us understand how Venus relates to other worlds in the solar system, right? So here's Earth, the Moon, Mars, Mercury, Venus, even Io. There are other worlds that made of rock and metal, just like there are, just like Venus is made of. And we have a great understanding of Earth and a pretty good understanding of the Moon. We've had humans to the Moon, the only other world where humans have gone to. We've sent lots of robotic spacecraft to Mars. We're sending more this year. NASA's Perseverance rover is going to launch in July. We've even had spacecraft visiting Mercury. I worked on a NASA mission for 4 years, Messenger, which was the first spacecraft to orbit Mercury. You have another mission to Mercury called Bepi Colombo on its way now. But I mentioned earlier in the talk that there was a time when we sent dozens of spacecraft to Venus, orbiters, balloons, even landers, But that interest has gone away, and the United States has not launched a mission to Venus in 30 years. And it turns out that it's not just about understanding Venus, but it's about understanding the other rocky worlds in the solar system. Venus really is the odd one out. But even more than that, it's about understanding the increasing number of rocky extrasolar planets or exoplanets that we're discovering. Because understanding Venus will tell us either it was or was not like Earth early on. And if it was like Earth, why and when and how did it diverge? And if it wasn't like Earth, well, then it'll tell us, is it more likely to get an Earth-like outcome for a world made of this material and this size? You look out your window, is that what's common in the universe? Or is self-cleaning oven and the pressure of a mile under the ocean, is that the common outcome? And does that tell us that Earth really is unique and not something we should take for granted? So understanding Venus will help us unlock the mysteries to understand the rules that govern Earth-like planets in general. And that is one of the most important reasons I think we should continue to explore Venus and go back there and try to answer the question, why is our sister planet not our twin? And that's the talk.
Thank you very much. Everybody, clapping hands emojis in the comments for Dr. Paul Byrne, planetary scientist from NC State University. That was mind-bending to think about. I was telling the folks watching at home while you were gone that when you showed that digital image, that artistic rendering of Earth with no water, that kind of got to me. You know, the way they sort of left the continents as we know them today, but then the oceans just drain, no water at all. Right. And to think that, I mean, in that future, even before that happens, there's not likely a life left on the planet. But that's kind of a harrowing future.
Yeah, this is kind of what gets the idea of understanding how precious Earth is in Earth Day and Earth Week, which is that we don't know how long life has been on Earth. We know that it's probably been a few billion years. We think we have fossils going back 3.4 billion years. There's some kind of debate as to whether or not there might be fossils even older showing life. It's extremely difficult to go back that far and be definitive about anything. But we do know that for a while, Mars may have had habitable conditions on the surface. Now, habitable conditions is a whole nuanced conversation that, it's a whole hour to talk about what we mean with that term, and not everybody uses the term the same way. And just because something is habitable does not mean that it is inhabited. But it's possible that early on in Mars's life, Mars may have had conditions a bit like Earth today. And I've shown here that it's possible that Venus is. I mean, I'm saying the word possible all the time because we don't know. But Mars is no longer capable of supporting life, and as we know it, and Venus certainly isn't. And it kind of speaks to this possibility that maybe for a while a lot of planets are, and then something changes or doesn't change, and they lose that capability. They lose the status of being habitable. And it may be that the same thing will happen to Earth. Earth was not always habitable. In fact, Earth went through a very traumatic experience 2.5 billion years ago called the Great Oxygenation Event. And prior to that, there was no free oxygen in the atmosphere. And there was life about 1 billion years before that, but oxygen was a poison to it. And now oxygen is the thing we all need, right? Almost all life, not all, but almost all life on Earth is aerobic. It needs oxygen. But that was a poison for the stuff that lived here beforehand, the bacteria that was here beforehand. So the idea is, planets can go through these pretty traumatic events that, we look back and go, it's great that we have oxygen. We have trees and birds and us, and it's nice. But, that wiped out a bunch of stuff 2.5 billion years ago. So, planets can go through these big changes and these environmental changes that really do threaten the stuff that's there. They do threaten the status quo. And whatever about human-driven climate change, I think this is telling us that really matters to our environment, to ourselves. Because here's the thing, Venus has an environment. Earth, whether it's human-driven climate change or the sun burns off the oceans, Earth is going to be fine. It doesn't care. It's a planet. But the environment that, whatever's living on the surface needs, is very vulnerable to those changes. And I think understanding the potential history of Venus and the potential future of Earth, and this is not to say this will happen, we just think it might, really, I think it tells us that Earth is a valuable resource, and we should understand it, and we should try to protect it. And we should understand how common or not this outcome is. If we're serious about looking for life on other planets and other solar systems, well, it's important for us to know. If we find a rocky world about the size of Earth, is it going to be like Earth, or is it going to be like Venus?
You mind taking some questions from the chat?
Yeah, please.
All right. Do we have a lot of actual flyover imagery of Venus, or is it mostly computer composited?
So we do have a lot of real images, yeah, but unfortunately they're not regular photographs because we cannot photograph the surface through that thick atmosphere. Visible light will not get through. So we have to use radar. So they are computer processed because that's how we process the radar data, but we do have radar images of the surface of Venus. Yeah, we do. It's not the same resolution as some of the data we have from the moon or Mars. So we don't have the fine scale stuff, but we do know roughly what the surface looks like. Absolutely we do, yeah. Now again, those data are 30 years old. It would be pretty nice to go back and get newer versions of it and see if anything's changed in 30 years. But yes, we do have radar images from most, about 98% of the surface of Venus.
Dennis has asked, would you describe exactly what killed the original landers on Venus's surface? How did they die?
Right, so they basically just, I was gonna say boiled to death, that's not quite true, but it was the heat that killed them. So it turns out operating at 90 bars, about 90 times Earth room temperature, or room pressure rather, that's about a kilometer under the ocean. And we have submarines, you know, specialized bathoscopes and robotic probes that can handle the pressure. So pressure is a problem, but it's an overcomable problem. The real problem is the temperature, because when you're on the surface and it's about 470 Celsius, it's just so hot. And especially if you need your instruments to operate at room temperature at 20 Celsius, you have to find a way of keeping those instruments cool. Whereas if you're in space, you are the warmest thing in space for huge distances. And if you need to keep cool, you can just vent your heat into the spacecraft and then that into space. That's not a problem. You can radiate it away. But on the surface of Venus, you can't. And so one of the ways around that is you can fill your spacecraft or your lander with we call it a phase change material. It's usually some kind of wax. And you basically fill the entire pressure vessel in this wax, and your little robotic electronics live inside that wax. And the wax melts. The wax takes that thermal load for about an hour, however much wax you have. And eventually then the electronics get too hot. And within a few seconds, the heat just goes right up and they die. NASA Glenn, which is really exciting. NASA Glenn for the last few years in Cleveland has been developing technology where you could make wires and transistors and stuff operate at Venus temperature. And they've now gotten wires to operate at Venus temperatures for about 6 months. So in the next 10 years, hopefully we'll start to see new technology come on stream that you absolutely could operate on the surface of Venus for months. Maybe not rovers, but maybe stuff you could land that would be able to take photographs and chemical measurements. And instead of hours on the surface, you'd get months. And of course, that would have all kinds of knock-on effects for firefighters and industrial applications on Earth. But that would really open up Venus in a whole brand new way. So hopefully in the next 5 or 10 years, we'll start to see that technology come on stream.
Yeah, Glenn was asking a similar question that you may have just answered, which was, how can we learn more about Venus when we can't get a lander on the surface for any length of time?
Yeah, that's a good point. And for a very long time, we were kind of limited by that. But it turns out that over the last 20 years or so, our spacecraft technology generally has just gotten incredibly advanced. So, for example, there's a lot more we could do from orbit now that we couldn't do before. We could even look, so one thing we do on Earth, for example, is we use what's called INSAR, which is interferometric synthetic aperture radar. It's a form of radar technique. And we can use INSAR to look at how the ground on Earth is moving. We often use it to look at volcanoes because as volcanoes are getting up to ready to erupt, they'll actually inflate a little bit. And we can track that inflation to like sub-millimeter size on Earth. 20 or 30 years ago, we couldn't have that technology at Venus, but we could now. And so now we could send an orbiter to Venus where, you know, orbiting is okay. We've done that before. And we could actually look for stuff moving up or down or even on side to side on the surface. So that'd be a massive thing to look for. We could develop balloon technology. In fact, I think I mentioned the 2 Vega balloons operated in the 80s. They were 2 Russian missions that flew 2 French-made balloons. And those balloons only lasted for a few hours because mainly the orbiter, it wasn't actually an orbiter, the spacecraft that dropped them off was off its way to Halley's Comet. And so those balloons went around the side of Venus and it lost track with them. But there are mission proposals to fly balloons in Venus that would operate for months, that would have an orbiter relaying data back to Earth. And those balloons could photograph the clouds. They couldn't get to the surface, that's true, but they could tell you what the atmosphere is made of. They could even listen to seismic activity and listen to volcanoes erupting. So there's a lot of new science you could do with balloons, with new orbiters, higher resolution radar that didn't exist 30 years ago. Nothing's really going to be a substitute for getting onto the ground, but before we get there, there's an awful lot yet we could do with modern technology.
Another question that actually came to me on Twitter from the North Carolina Office of Environmental Education. Thanks for watching, y'all. Why historically Mars has garnered more attention than Venus?
So I'm going to make sure that I'm not going to get myself into trouble here. because there's a lot of it's sort of a loaded question. There are answers here that do not have anything to do with science and have to do with what we call programmatics instead. I do not know the answer to that question. My guess is that for a long time, Mars has occupied a special place in human culture, everything from War of the Worlds to the God of War, just for thousands of years. We had Venus, but we also had Mars, and people have been fascinated by Mars and the stuff that might live there. It's easier to land on Mars, and it's certainly easier to last for a long time on Mars than it is on Venus. You can image the surface of Mars because it has virtually no atmosphere. With a regular optical camera, you cannot do that at Venus. So for a whole pile of reasons, it's kind of easier to explore Mars. It is telling that I mentioned NASA's Magellan mission, which operated from 1990 to 1994, which gave us a full radar coverage. The year Magellan was turned off in about 94. Some folks were working on that in 1995. And then in 1996, asteroid or meteorite sample ALH 84001 turned up. And for those who might be listening and who can remember what that is, ALH 84001 was a meteorite from Mars discovered in Antarctica that was suggested to have microbial fossilized life in it. And now most people, me included, think that's not a microfossil. It's a naturally occurring thing in the rock. But that kind of garnered the whole world's attention in 1996. And the next year, NASA sent the Pathfinder mission, where it was the size of a large shoebox called Sojourner, was landed on Mars, and was the first rover on Mars. We followed up with Spirit and Opportunity in 2004. In 2012, we landed Curiosity, and in 2021, we're going to put Perseverance on the surface. So around the time that NASA's last Venus mission went away, NASA spent a lot of money and interest in Mars, and Venus has not really had a look in since then. So it's a function of kind of programmatics in terms of where people want to spend the money to do exploring, and also the logistical ease, relatively speaking, of Mars. Mars is extremely hard, but in some respects not as hard as Venus. So I think that's why. It's not because of any intrinsic scientific reason, I don't think. And particularly as we discover more and more Earth-sized worlds and around other stars, I think Venus, and I think this is already beginning to happen with scientists in the scientific community on Earth, we're beginning to recognize that maybe we should go back and pay a lot more attention to Venus than we used to, than we have for the last few decades, because it might really hold the key to unlocking the mysteries that govern planets this big.
So I'm curious about sort of what your work is like. Are you sorting through radar images of planets? Are you running mathematical models and computer models, based on numbers that you pull from that kind of data?
So it's kind of all of that. It's all of that. And there's lots of different kinds of planetary scientists. So I'm a planetary geologist by training. So I was trained on looking at rocks on Earth and understanding what that is. And most geologists look at Earth because that's where the jobs are. But one of the things that we've seen around the solar system is there are giant volcanoes on Mars, and we know they're volcanoes. Okay, we've never seen them erupt. But we have every reason to think there are giant volcanoes because they look like giant versions of the volcanoes on Earth. And there are impact craters on other planets, and there are no impact basins left on Earth, but there's lots of impact craters. And we didn't see them form, thankfully, because we don't have a recorded record of that happening. But we know they must have, because the moon has lots of craters. And so a lot of what I do is what we call comparative planetology. It's understanding other things and other worlds that we see through radar images or photographs or gravity data or chemical data or however we do it, and then trying to understand why it looks the way it does and what processes make it, by understanding what the same processes and landforms are on Earth. And vice versa, right? Like in the case of Venus. So Venus perhaps is giving us a glimpse of future Earth, and present-day Earth is giving us perhaps a glimpse of past Venus. That's that power of comparing stuff, but it all starts with taking observations, whether they're images or photographs of some kind. And then we do computer modeling, we can do laboratory modeling, we can do field work, we can go to places on Earth that we cannot obviously get to equivalents on other planets. But if we can understand and figure out why lava flow looks the way it does on Earth, we can then make some assumptions about similar looking lava flows on other planets. But it all starts with looking at these observations, yeah. And before we had these spacecraft, this was impossible. And it was really in the 60s, and mainly thanks to NASA, that we were able to start really understanding these points of light in space as worlds into their own right.
Thank you very much. Thanks for sharing with us. If folks are interested in this kind of work, what should they check out? Just browsing the NASA website, or are there better resources?
So NASA's a really good place to start because a lot of these resources are available. They're all free. In fact, I should say that even for scientists or interested folks, all the data we use are all publicly available. NASA puts everything up online. Sometimes they're kind of hard to find, but they're all there. They're there for the whole nation, the whole world, in fact, to use. But if you're interested, you can follow me on Twitter. I'm at the Planetary Guy, or you can Google me. You can get in touch via NC State. I work at NC State, and you can Google my email address that way. But just go online to NASA. Go to NASA's channels on YouTube. You can follow them on Facebook, on Twitter, on Instagram. They have dozens of different accounts. And then if you're interested in Earth observation or climate change, if you're interested in spacecraft exploration or human exploration, the Artemis program. In fact, next month, May 27th, SpaceX is going to launch for the first time since 2011 American astronauts from American soil from the Cape. You can follow all that online too. So this is a really exciting time. In July, NASA is going to be launching the Perseverance rover, which is this nuclear-powered car-sized rover. We're going to fly to Mars. It's going to get there, and it's going to be dropped onto the surface in February by this crazy-looking thing called Sky Crane. Just go to YouTube and Google Perseverance rover. So there's a whole pile of resources online for folks to find. Absolutely.
Excellent job tonight. Thank you so much for being here.
Thank you, and thanks for putting up with me and my parakeet. It's live TV, right? So
we managed it. We managed it. If you go back and look at the YouTube chat, you can see folks were very kind to chat with me and answer some of my questions, like if you could avoid the heat and pressure, would you visit Venus and walk around in that special suit? And the answers were interesting. Some folks were like, yeah, I guess that I would. The resources might be better spent on, actual exploration robots and things that'll give us more data than just, Chris walking around on the surface.
I would certainly give it a go, but I would want someone else to go first.
Right, exactly. Sure. That's a good point. That's a good point. Well, everybody, thanks for tuning in tonight for our Virtual Science Cafe brought to you by the North Carolina Museum of Natural Sciences. Thank you, Dr. Paul Byrne. I want to send a special thanks to the North Carolina Office of Environmental Education for making this so cool connection between the museum and Dr. Byrne so that we could bring him here into the Virtual Science Cafe. Thanks much to you folks. And thanks for tuning in. Keep an eye on naturalsciences.org or the museum's website to see what events are coming up in the future. For example, tomorrow, April 24th, is the 30th anniversary for the Hubble Space Telescope. So at noon here on the museum's YouTube channel, and I think on Facebook as well, we will be live with museum astrophysicists, Dr. Rachel Smith and Dr. Patrick Troithart, who are going to talk about their work and how it relates today to the Hubble Space Telescope. Stars, planets, galaxies, and all of the above. So don't miss that. Bookmark that. Noon right here tomorrow, Friday, April 24th. And follow the museum, of course, on social media, Facebook, Twitter, and Instagram. We're at Natural Sciences. And if you like the kind of stuff you're seeing here at the museum's YouTube channel, then, of course, like the videos, subscribe, click the notification bell. That lets you know when we're giving you all the free, cool science stuff that you know and love from our museum. So, again, I'm your host of the Science Cafe. My name is Chris. Thanks for tuning in, everybody. We'll see you next time. Good night.